Okay, hello everyone. So, moving on to a new topic, lenses and optical instruments. So, these are the smaller topics we'll be discussing. Lenses are simple optical instruments, mostly made out of glass. And we're going to talk about two types. One with this shape, piece of glass made into it's like two circles, two parts of two circles joined together. So this shape is called, one that bulging outwards, convex. This is actually double convex. One that bending inwards, called concave. And when light passes through these, they bend. It's diffraction, right? Light coming from air, getting into a denser medium. So because of that, it's going to diffract. It's going to bend. This bending process can focus light into a point. So that's how that's the use of the lens, right? It diffracts light, and because of the shape, you can focus light into well-defined point. So we'll get into more details soon. Let's see what the next slide says. Excuse me. Thin lenses. So we will mostly talk about thin lenses. There are thick lenses also. For our ray diagrams and all that, we will stick with thin lenses. Those whose thickness is small compared to the radius of curvature. What is that? So here's a lens, and the radius of curvature, this radius of the circle, compared to that, the thickness is small. If you think about something like this, right? A much thicker lens, radius will be, if you complete the circle, it will be something like this. So here's the radius, and the thickness of the lens also very comparable. So we're not gonna look, there are certain lenses like that, but we will stay with the thin ones and the applications. We can name them into two categories: converging and diverging. A lens that focuses incoming light into a single point is a converging lens, and one that spread light into a wider angle is a diverging lens. Now we talk about converging and diverging mirrors. Right? If you remember, this concave. Now we are talking about mirrors. This is a converging mirror. This one, convex, is a diverging mirror. Now this is reflection. Right? Light comes in, it reflects in a converging manner and in a diverging manner. When it comes to the lenses, the light does not reflect, it actually goes through it and it bends, and then based on how it bends, we can label them as either converging or diverging. One thing to remember, when it comes to lenses, they're kind of the opposite of the mirrors. A concave mirror is a converging mirror. A convex lens is a converging lens. Alright, and goes same for the diverging ones. Okay, so we're going to start with convex lenses. Again, if you go back to reflection, remember that concave mirrors had so many different ray diagrams. Based on where you place the object, you get different images. The real ones, virtual ones, bigger, small, upside, upright, upside down, like that. That's concave mirrors. When it comes to lenses, it's the convex lens has all these properties. Convex lenses can make so many different images. Concave lenses have only one type. It's like the convex mirror. So it's like this: lens and mirror, concave, convex, concave, convex. Kind of, this is the connection, right? Okay. All right. So let's start with the convex lens, the one that has all these different applications. So here's that. Again, we draw a line through the center to represent where the lens is, and then we draw this principal axis. So here in the diagram you can see the light that comes parallel to the principal axis converge, they bend, they diffract, they bend, and goes through one point, which is called the focal point. So if light is coming from this side, we usually mark the focal point on the other side. Okay, see what else we have. Also you can see we have parallel light coming in, but the light is not parallel to the principal axis. They're coming from a side, but still they meet at the same line along the same focal plane. Right? So these kind of lenses are called converging lenses. Convex lenses are converging. And here the diagram you can see the focal length, the focal point, and these have positive focal points of positive focal length. It's on the other side. It is the direction that light is actually traveling. Right? This is real light coming in, and it goes to the other side. So you measure the focal length in the direction the light traveling. It's a positive focal length. Let's check the other type. So here we have a diverging lens, concave lens. One with just one single application, one type of ray diagram. So this is the lens, principal axis. Light comes parallel, diverge, appearing light coming from a point over here. Comes in, diverge, appearing light coming from this point. This is the focal point. The distance is the focal length. This is a negative focal length, right? If the focal length is in the same side, like where the light is coming in. Now this one, this is the side light coming in. This is the side that light, after bending, this is the side light enters, right? So this is a positive focal length. This is a negative focal length. So we'll talk about this negative positive difference again in the sign convention, but you just have to remember that it's the opposite for the mirrors. When it comes to lenses, there's another important factor we define. It's just the focal length, but 1 over focal length, we call it the power of the lens. P equals 1 over focal length. Lens power is measured in a unit called diopters. This may be a little familiar term because usually if you're wearing glasses or lenses for reading and all that, normally you talk about your power has changed, or doctor will recommend you need to have certain power in your lens. That's actually 1 over focal length. That's an optician's thing that they prefer to talk about diopters, power, 1 over focal length. So for an example, if your f is, let's say, I don't know, this is a random example. 20 centimeters, what's the power of this lens? So power will be 1 over 20 cm, or 1 over 0.2. What is 1 over 0.2? Oh man, I need a calculator for that. 1 divided by 0.2 is 5. The power is 5 per meter. That's the power. Alright, let's move on, see what else we have. Some points important in drawing ray diagrams. Let me erase this. Let's work on few ray diagrams. How do we draw the diagrams for convex lenses? How do we find the image? Kind of similar to lenses, mirrors. Only thing is light does not reflect, it goes through the lens. So let's start with convex. One second. Convex. Alright. Principal axis. You mark the lens. Then you can just represent the lens with a very small diagram picture like this. What matters is this line where you make all the measurements. So here we have an object. The light that comes parallel to the principal axis, this is the focal point, bends and goes through F. The parallel light bends and goes through F. Remember, in the mirror it reflects and goes through F. Here it bends and goes through F. We can mark the same focal point, that same distance on this side. Even though this is the actual, the positive side is this, we just mark it on the other side also. It's kind of a standard that we mark focal point and the point C, the curvature point, the radius point on both sides. So the light that goes through F on this side bends and comes out parallel. So where they meet, here we have the image upside down. We can get a third point, third one. The light that goes through, okay, let me move this color editor. Oops. Light that goes through the center of the lens goes without bending. And that should also go through this same point. Alright, so basically we use three lines. The parallel one bends and goes through F. One that goes through the center does not bend. One that goes through the F in the other side comes out parallel. Okay? Alright. What else we have? Conceptual example, half block lens. What happens to the image of an object if the top half of the lens is covered by a piece of object? So something like this. So here let's say you have a lens and you have an object. We cover this portion by a piece of cardboard. Will this make an image? What do you think? What will happen to the image? Will there be an image? Something to think about. Okay, moving on. Diverging lenses. Alright, let's clear this. Diverging lenses have less applications, mostly just one image, one type of image. Principal axis, and you place the lens. Again, you mark F on both sides. Object. Okay. Light comes in, diverge, goes away from the principal axis, appearing light coming from a point over here. One that goes through the center does not bend. One that goes through the center. So where they meet, here we have a small image. Now you can see it's small, it's upright, it's virtual. Why do we say it's virtual? We are looking at the object from this side, right? If we go back to the previous slide, light needs to enter the eye in order to create an image. So here you're looking at something through the lens. The object is over here. Imagine you're looking at something using a magnifying glass. You keep object on one side, then the lens, then your eyes. Right? Magnifying glass is not the right example, but just for the time being. So the light needs to go to your eye and they need to meet at some point in order to create an image. So here the light intersects over here, the point where the image is, goes to your eye. So you see the actual real image. So these are real images. If we go back to the other side, lens. Light comes into your eyes in a diverging manner. So you trace it back until it meets and it creates an image on the same side. Now this is a virtual image because there is no real light here. We just extended this pink color line was we created that, our eye created it, right? Okay. So this is a virtual image. And these are the type of images the concave lens makes. And we have the same equation. The equation when we use with mirrors, we can use the same thing for lenses as well. We call it thin lens equation. Over there we call it mirror equation. There is another equation for thick lenses. We're not going to go into that, but if you're getting into advanced optics, if you're going to become an eye doctor or somebody like that, you will learn much more complicated equations, but this is the starting point. Okay. So everything else same. Object distance, here the object, so here, everything measured from this dotted line. So we have DO, it creates an image over here, DI, and height of the object HO, height of the image HI, focal length F. Alright. So the sign convention, things to remember. Focal length is positive for converging, means converging means convex lenses. Convex lens F positive. Concave lens F negative. Object distance is positive when the object is on the same side as the light entering the lens. That is usually all the time that's the case. Light is entering the lens from this side, in this case left side, light is coming in. object is in the same side. So this distance is a positive distance. The image distance, this is the one that is in conflict with mirrors. The image distance is positive if the image is on the opposite side from the light entering the lens. Little complicated line, but read it again. Image distance is positive if the image is on the opposite side from the light entering lens. So light is entering from the left side, it goes into the right side. If the image is over here, which is in this case, this is a positive image distance. So going back to the previous one, this is a negative image distance. Height of the image is positive if the image is upright, negative otherwise. So this image height is negative because it's upside down. This image over here, HI, is positive. So the magnification formula stays the same. Magnification HI over HO, and then the negative DI over DO. Power of the lens is positive if it is converging. Convex lens, positive power. Concave lens is negative power. Okay, some advice on how to solve these problems, ray diagrams. Let's try an example. Right?